Let me give you some shapes of position time graphs. I want you guys to tell me what those shapes of position time graphs mean. First one, these are all position time, by the way, position on the y-axis, time on the x-axis. Tell me what that one means, please. Straight line, Bo. So what does that mean? Good. It's a constant velocity because it's a straight line. It's a negative velocity because the slope of it is negative. It's sloping downward, right? So it's a constant negative velocity. What about this one? Position time graph where the line itself on the graph is curving upwards. What does that one mean, Hayden? Good. It's speeding up. It's acceleration. What does this one mean? Where we have a straight line again, but this time it's a flat straight line as opposed to a straight line that's going down or upwards. Fraser? Good. Standing still, or the object is stopped. Or you could say a constant velocity of 0 meters per second. Good. What about this one? We have a straight line again. Every time we have a straight line, what does it mean? Good. It means a constant velocity every time we have a straight line. In this case, as you said, it's a constant positive velocity. In other words, it's moving forward, right? It's moving in a positive direction. What about this one? Notice that my position is positive in each case. So it's not like I'm behind where I started or whatever. What does this one mean? Oh? It's a deceleration. What's another term for that besides deceleration? Negative acceleration. Good. What's another term for it besides deceleration or negative acceleration? Slowing down. Any of those things would work. Okay? If I give you a quiz on this, say, tomorrow, then you would tell me that it's a negative acceleration. You could tell me that it's slowing down. You could tell me that it's deceleration. Got it? All right. What if I give you a position time graph that looks like this? Make it a little bit bigger this time. A position time graph that looks like this. And I asked you in the first stage, we'll call it stage A, to find the velocity of it. The velocity of stage A, the entire stage. Anybody know how to do it? Rutger? No. Velocity isn't up and over. Tell me what is up and over. Okay, Rutger made a mistake that anybody can make here. Okay, that's a pretty common mistake. You want to find the velocity here, and we say it's up and over. Well, velocity is not up and over, but something is. What is up and over? No, but you're close. Good. Up and over is position. If I want to go find the position at this moment in time, then I can go up and over. That position will be at that moment in time. So up and over on a position time graph is going to be position. Now, we haven't done velocity time graphs yet. We will in a few days. You want to find the velocity on a velocity time graph? It's going to be up and over because it's the variable that's on the y-axis. A position on a position time graph, up and over. Now, the original question again was, how do we find velocity? The velocity of that entire interval. Yep. Good. The equation for velocity is displacement over time. Well, how do we find the time? That's easy, right? The time is easy. We just take it off of the x-axis. How do we find the displacement? Yep. Good. Final minus initial what? Nope. Close. Position. Final minus initial position. So, in order to get velocity, we need displacement. In order to get displacement, we need position. And to get position, is somebody, I can't remember who it was, told me already, to get position, we go up and over. Does that make sense? All right. What would be the velocity of stage B? You can give me a number for that right now, even without any numbers on our y-axis here. Hayden? 0. Okay, how do you know it's 0? Anybody tell me how you know it's 0, even without any numbers on the x or y-axis? When we were going over the shapes, Aiden, we saw that a straight, flat line meant Yeah, it meant that it was stopped. It meant that the velocity was always 0. Good? All right. I showed you a minute ago a graph that looked like this, and we said that that meant acceleration. It meant speeding up. Today we're going to focus on that acceleration, not specifically for these graphs, but rather with equations for word problem type questions. We're going to define acceleration, first of all, as the rate of change of velocity. How quickly the velocity is changing. It's not what is the change in velocity. Okay, I can go from 0 to 100, and my change in velocity is 100. But that's not my acceleration. That's not how quickly the velocity is changing. When we measure acceleration, we want how quickly the velocity is changing, the rate of change of velocity. Now, anything that's a rate, you're going to learn this through Physics 20 and through Physics 30, anything that has the word rate in its definition is going to be divided by t. Velocity is the rate of change of position. It's change in position over t. Power, you're going to learn later on, is the rate of change of energy. It's change in energy over t. Acceleration is the rate of change of velocity. Acceleration is going to be change in velocity over t. So the main equation for acceleration is delta v over delta t. Change in velocity, not change in speed, but change in velocity over change in time. Now, can anybody tell me what the units would be for acceleration? The easiest way to figure them out is to take a look at this equation. What are the units for change in velocity? You guys know that, right? What are the standard units for velocity, or for change in velocity for that matter? Right here? Meters per second. Good. So the units here would be meters per second over, what are the units for time? Seconds. So it's going to be meters per second per second. You can write it like that. That's fine. Most people don't write it like that. Most people simplify it by writing it this way, meters per second squared. But they both mean exactly the same thing, so whichever way you write it are both correct. Can you tell me if acceleration is a vector or a scalar? Okay. It's a vector. Yeah, how do you know? Good. Good. That's the first way, in fact, the most important way that you can determine that acceleration is a vector. If it involves velocity, and velocity is a vector, then it's got to be a vector itself. So acceleration is a vector. Now, if you didn't spot that, how else could you tell by looking at this equation that acceleration is a vector? It's got the arrow sign over it, right? The half arrow, which is the vector sign. Anytime you see something with a half arrow over it, it's got to be a vector. Now, you've just learned your second equation. The first one was v is equal to delta d over delta t. The second one is a is equal to delta v over delta t. You are about to learn a bunch more. All of the equations that I'm about to show you are valid whenever a problem involves acceleration. From now on, when we see a problem, we're going to have to identify whether it involves constant or average velocity or it involves acceleration. If it involves constant or average velocity, we're going to use v equals d over t, the equation that we learned the first day of class. If it involves acceleration, speeding up or slowing down, then we can use the equation that we just learned or one of the other ones that I'm about to write down right now. Besides a is equal to delta v over delta t, we also have d is equal to VIT plus 1/2 a t squared. That's kind of an ugly looking equation. VIT plus 1/2 a t squared. What's VI stand for? Yep. Good. Initial velocity. T stands for time, obviously. A stands for acceleration. So the displacement of an object as it accelerates is equal to the initial velocity times the time. plus 1/2 of the acceleration times the time squared. Here's another one. It's real close to the one we just wrote down. D is equal to VFT minus 1/2 AT squared. The only difference here is the minus sign and the VF is subbed in for VI. What's VF stand for? If VI is the initial velocity, then VF is the final velocity. Good. Here's another one. VF squared is equal to VI squared plus 2AD. A stands for acceleration, right? D stands for displacement. What's VF stand for? Who thinks they know what VF stands for? Fraser? No. I knew somebody was going to, whoever raised their hand, I knew was going to answer final velocity. You're so close. You are so close. Final speed. Hey, how do you know it's final speed, not velocity? Because there's not the little vector sign over top of it, right? Does that make sense, Fraser? Okay. So it's final speed, not final velocity. What does VI stand for? Initial speed, not initial velocity. All right, one more. D is equal to VI plus VF, initial plus final velocity, over 2 times T. Notice this last one doesn't even have the term acceleration in there. It has displacement and initial velocity and final velocity and time, but it's still valid when a problem involves acceleration. Yep. Yes. Yes, you will. Yeah. So now whenever we see a problem, a word problem that we're trying to solve, I want you to look at it and ask yourself, does this problem involve constant or average velocity? Or does it involve acceleration, speeding up or slowing down? If it involves constant or average velocity, we're going to call it a group A problem, and we're going to use the equation V equals d over t. Either displacement over time or distance over time, depending on whether we're looking for speed or velocity. So if it involves constant or average velocity, you're going to use this equation, and we're going to call it a group A problem. If it involves acceleration, speeding up or slowing down, we don't know which equation we're going to use, but we know we're going to use one of the red squared off equations here. We're going to call those our group B equations. Constant or average velocity, group A. Acceleration, group B. Now, how do you know which equation to use from our 5 group B equations? Got 5 of them. How do you know which one to use? We got constant velocity. We know we got to use V equals d over t. We got acceleration. We got 5 options. Write down your givens. Compare your givens with the equations that we have up there in group B. And then look at which one fits the best. Simple as that. Let's take a look at an example that's on page 47 of your textbook. You don't need to copy this example out, but I do want you to copy the solution out. Write down as you're starting this, write down 1.12, page 47, so that you'll know where to go back to find the question. The question says, a hybrid car with an initial velocity of 10 meters per second to the east accelerates at 3.0 meters per second squared to the east. How long will it take the car to acquire a final velocity of 25.0 meters per second to the east? Here's what I want you to do first. Okay, when we did our last problem, sets of problems, a couple of days ago, our constant velocity problems, I said, first thing you should do is write down your givens. I'm changing that now. Now what I want you to do first is identify whether it's a group A problem or a group B problem. Group A, constant or average velocity. Group B, acceleration. What is it? Is this a group A or is this a group B? Group A or group B? Group A, constant velocity? Group A is constant velocity. Group B is acceleration. So is it accelerating or is it traveling at the same speed the whole time? It's B. Yeah, it involves acceleration. Now, it doesn't mention the word accelerate. Actually, it does. But even if it doesn't, okay, even if it doesn't, if we're going from 10 meters per second to 25 meters per second, we know that it's accelerating, right? So we know it's a group B problem. If we know it's a group B problem, now we can write down our givens, and then we can take a look at those 5 equations that we have within group B and see which one fits the givens the best. So now let's write down those givens. We have an initial velocity, we'll call it VI, of 10.0 meters per second. We'll say east is positive, so VI is simply positive 10.0 meters per second. We know that VF is 25.0 meters per second. And it's also east, so it's also going to be a positive value. A, the acceleration, is 3.0 meters per second squared. Can you tell me what it is we're looking for here? How long will it take the car to acquire a final velocity of 25? What are we looking for here? Look like you're ready to give me an answer there. Not the final time, but you're close. Just the time interval. Yeah, the total time interval, delta t. All right, so we have VI, we have VF, we have A, and we have T. Let's take a look at that list of equations that you just wrote down in your notes and see which one fits these givens the best. Okay, the first option that we had was A is equal to delta V over delta T. Let's take a look at that one. Does it seem to fit? We have A. We're looking for T, so that counts. Do we have delta V? No, but we have VF and VI, right? That's pretty much like having delta T, right? Or delta V, I should say. Does this equation work? Sure. Let's just use the first one. We know it's a group B problem. We know we can't use V equals D over T. The other ones are all valid. Just use whichever one fits. Well, in this case, the first one fits. Now, we have to rearrange this to solve for T. How do we do that? How do we do that? What do we got to do first? Let's not worry about that quite yet. Okay, let's not worry about final minus initial velocity yet. Bailey? Yes. The variable you want to solve for has to be on the top. If it's already on the top, that's great. Go to step 2. If it's not on the top, then get it to the top. And Bailey said we're going to get it to the top by multiplying by A. We multiply, why? Because it's divided. So on the right-hand side by dividing, let's take it to the left-hand side by multiplying. A times T is equal to delta V. Now, it's still not by itself, but the first step was to get it to the top if it wasn't there already. Now we've got it to the top. So now we'll go to step 2. Step 2 is get it by itself. Get it to the top, then get it by itself. How do we get it by itself here? A is multiplied by T, so we're going to do what? Yeah, we're going to divide the A out. Good. Delta V divided by A. Now, delta V is 25 minus 10. A is 3.0 meters per second squared. 25 minus 10 is 15. 15 divided by 3 is 5. And what do the units for time end up being? Seconds. How many digits should my final answer be? Let's take a look at our data. This one has 3 digits. This one has 2 digits. This one has 3 digits. Final answer should be 2 digits. Good. 5.0 seconds. So now we've just opened up a whole new world, right? Up until now, it's been one simple equation, v equals delta d over delta t. Now it's 6. All of a sudden, in a span of about 10 or 15 minutes, it goes from one equation to 6 equations that we have to pick from. But it doesn't have to make it hard. First of all, identify whether it's group A or group B, constant or average velocity, or acceleration. If it's group B, write down your givens, and then see which of those 5 equations in group B fits the best. In this case, it was the very first one. Next time, it might be the third one, or whatever. All right? Let's try these 2 questions at your desks right now. Do what you can, including the entire process that we just went through. Identify first whether they're group A or group B. Once you've done that, assuming they're group B, then write down your givens and determine which of the group B equations fits. Then write down the equation, then sub in your values, get your answer. If you're having trouble with it, stop me as I'm walking around and I'll give you a hand. All right, I want to do both questions here now that you've had a chance to work on these. Question number 1 says, a motorcycle with an initial velocity of 6 meters per second to the east accelerates at 4.0 meters per second squared to the east. How long is it going to take to reach a final velocity of 36? First thing we do, what's the first thing we do for this question? Group A or group B? What is it? Is it group A or is it group B? Cassidy, it looked like your mouth was starting to move there. Is it group A or is it group B? B, good. It involves acceleration. We're speeding up. Even if it doesn't mention this word, even if it doesn't say this, okay, you can't see that for whatever reason. Okay, we know we're going from 6 to 36. Clearly that involves speeding up. It involves an acceleration. So it is a group B equation. I saw, as I was walking around, I saw Rutger physically write down that it's group B. You don't have to physically write that down, but I think it's a good idea. At the very least, you want to identify that it's group B. Once we know that it's group B, we can take a look at those 5 equations that we have from group B. A is equal to delta V over delta T, VF squared, so on and so on and so on, and see which one fits the best. Which one does fit the best for this question? I think it's the first one again, right? A is equal to delta V over delta T. The bottom line is, you got to look at it and say, do I have all the variables in there? Or do I have, or am I looking for all the variables in there? Do I have A? Yes. Do I have delta V? Well, not exactly, but I have VF and VI, which is pretty much the same thing. Do I have T? No, but that's what I'm looking for. So it is going to end up being that equation. Should have wrote down my givens first, actually, shouldn't I? It is going to end up being that equation. We're going to say east is positive. VI is 6.0 meters per second. VF is 36. And A is 4.0. We're looking for time. So when we look at that first equation again, A is equal to delta V over delta T, we can see that we either have or are looking for all of the variables in that equation. We have A, we have VF and VI, we have, or we're looking for T, so we're good to go on that equation. Now we want to rearrange it to solve for T again. Even though we solved for the same variable the last time, let's go through that process again, just to refresh your memory on that. Got to be on the top, that's step 1, right? It's got to be on the top. I think it was Bailey that told us that, right? We had to get it to the top. How do we do that? Multiply both sides by delta T. Okay? The effect of that is that the T goes up to the other side by multiplying. So now we don't have T by itself, but at least step 1, get it to the top is done. Now we got to get it by itself. Get rid of the A. How do you do that? Divide both sides by A. T is equal to delta V over A. Now, delta V is 36.0 minus 6.0 over an acceleration of 4.0. So that becomes 30 over 4, which gives me a time of 7.5 seconds. How many digits should my final answer be? How many numbers should it be rounded to? Let's go back to our data. This is 2, This is 2. This is 3. Final answer should be 2. Good. How many people got that one? Excellent. Excellent. Now, number 2, let's read that one. This one says, an elk moving at a velocity of 20 kilometers per hour accelerates at 1.5 meters per second squared north for 9 seconds, 9.3 seconds, until it reaches a maximum velocity. We want to know what that maximum velocity is. And we're not going to worry about the whole kilometers per hour thing right now. Is this a group A or group B? Are we constant velocity or are we speeding up? We're speeding up here, right? Okay, we want to find out what that final velocity is, how fast that elk is moving after it accelerates at 1.5 meters per second squared. It's a group B problem. We're going to say VI is 20 kilometers per hour. Say north is positive, first of all. VI is 20 kilometers per hour. We're going to say that A is 1.5 meters per second squared, and that T is 9.3 seconds. What are we looking for here? What are we trying to solve for? The maximum velocity. What variable is that? Yes. Okay. When do you reach the maximum velocity? At the end, right? If you keep speeding up, when are you going the fastest? At the end. The final velocity. So we're looking for VF here. Now, there's a couple of things that we've got to be conscious of here. The fact that we're looking for VF, which doesn't actually appear in this equation. But the other thing is that we want to be in standard units here. Every time we're dealing with acceleration, we don't want to be in the old units of kilometers and kilometers per hour. We want to be in standard units, meters per second. So we have to convert this kilometers per hour to meters per second. We've done that before. I don't want the answer here yet. How many meters in a kilometer? 1,000, good. So that means 20 kilometers is 20,000 meters. How many seconds in an hour? 60 times 60, yes, which is 3,600. So let's say instead of 1 hour on the bottom, we have 3,600 seconds on the bottom. What does that work out to be for a velocity in meters per second? Someone's got to have that. 20,000 divided by 3,600? Yep. 5.5556 meters per second. We're going to go with 4 or 5 decimal places until it's a final answer. Okay, ideally, you'd keep the 10 decimal places your calculator has, or whatever. That's not practical to write down every time, so let's write it down to 4 or 5. All right, let's look at our equations again. I think we're going to use that same one again. A is equal to delta V over delta T. Do we have A? We do. Do we have delta V? We have VI, and we're looking for VF, so that counts. Do we have T? We do, so we're good to go there. Let's rearrange it to solve for delta V first. It's already on the top, so I can skip that first step. But I do still need to get rid of T. T is divided by V, so how do I get rid of it? Take it to the other side by multiplying. Good. Delta V is equal to A times T. Let's multiply those numbers together and see what we get. 1.5 times 9.3. That's going to give me 4.515, 13.715, 795, 13.95. Okay, thank you. 13.95 meters per second. Is that my final answer? Am I done? What have I just found? I haven't found my final velocity. I've found the change. Let's get the final now. We know that delta V is equal to VF minus VI. Want to solve for VF. How do you get rid of the VI? Yep. Add it up. Add it to the other side. Delta V, let's say VF is equal to delta V plus VI. Delta V is 13.95. VI is 5.5556. What do we end up getting there? 19 point. Where would we round that to? How many digits? 19.5056 should be rounded to, well, this is 2 digits. This is 2. This is 2. Final answer should be 2 digits, which would make it 20 meters per second. It asks you for the answer in kilometers per hour, but again, I don't really care about that right now. We'll deal with that later on. Okay, if you get meters per second, that's good. How many people got that one? Either the 70 kilometers per hour or the 20 meters per second. Okay, a little bit less, but it was a bit of a tougher question, hey? Make sense now? The big thing was that delta V equals VF minus VI that people probably forgot there. Okay, if you've got that copy down, I want to do one more example here. It says a cattle train traveling west at 16 meters per second is brought to rest in 8 seconds. What's the displacement of the cattle train while it is coming to a stop? How far does it move as it's stopping? Group A or Group B? Does this involve constant or average velocity, or does it involve acceleration? It involves acceleration. Even though it doesn't mention the word acceleration, that's okay. We know it's slowing down. That's acceleration. That's a Group B problem. Now let's write down our givens and see which of the Group B equations seems to fit those givens. Let's define west as positive, okay? We could define east as positive and make everything negative, but since it's not changing direction, it's always going to the west, it's probably easiest to make it positive. You guys are going to give me some givens this time. What is this 16? Is that going to be V or delta V or VI, or is it VF? Yep. That's the initial velocity. That's VI. And it does have that vector sign over it because it is velocity. It does have direction. Good. Tell me something else. Tell me something I don't know now. Tell me something else. Good. Reading between the lines here. Excellent. VF is equal to 0. How do you know that? Good. It's brought to rest in 8 seconds. It stops in 8 seconds, so therefore VF has got to be 0. Sometimes you got to read between the lines like that. All right, tell me something else I don't know. What's this 8 seconds thing? That doesn't sound very hard. What's 8 seconds? On a count of 3, everybody say it at once. 1, 2, 3. See, I told you knew it. I knew you knew it. Then just put up your hand and say it, okay? 8 seconds is time. Good. Delta T. Not TI, not TF, delta T. What are we looking for here? What are we looking for? On the count of 3. 1, 2, 3. We got some people whispering on that one, hey? And I hear a couple different things that people are whispering. I heard displacement, acceleration. What is it? Find the displacement. Looking for displacement, right? Delta D. All right. Let's take a look at those equations that are all Group B equations now and see which one fits the best. I'm going to write them down real quickly here again, just so that we can refer to them. Delta V over delta T. Does that one seem to work? Do I have A? No. Do I have delta V? Yeah, VI and VF. Do I have T? Yes. Does that one work for us? No, because there's something I don't know. Right? A is irrelevant in this question. So that one's not going to work. Let's try VF squared is equal to VI squared plus 2AD. Do I have VF? Yeah. I mean, I need final speed. I've got final velocity, so that's good enough. Do I have VI? Yeah. I need the initial speed. I know the initial velocity is 16 to the west. Okay, that's more than I need. Do I have A? No. Do I have D? Yeah. I could find A there, right? I could solve for A, but that's not what I'm looking for. So it wouldn't be wrong. If you use that equation, and sorry, I don't have D either, do I? So I couldn't solve for A because I'd end up with two unknowns. That's not very helpful to me. So we got to try another one. Yep. Yeah, we'll go there in a minute, okay? Okay. Fraser, that's a really good point, but we'll deal with that in just a minute, okay? Let's try another one here. Let's say D is equal to VI plus VF over 2 times T. Do we have D? We're looking for it, right? Do we have VI? Yeah. Do we have T? Sorry, VF? Yeah. Do we have T? Does that one work? Sure it does. And so I went through 3 of them before I found the one that works, but that's okay. D is equal to VI plus VF over 2 times T. VI is 16 plus 0 over 2 times 8. And the answer is 64 meters. We're going to round that to 2 digits because my least precise piece of data was 2 digits. Now, Fraser made a really, really good point here. Okay, I've told you that all of these equations are valid in a Group B problem. You're allowed to try any one you want. Okay, if you try the first one, you're going to solve for acceleration, which is not what you're looking for, but it's not wrong. You've just solved for something you're not looking for. It's still perfectly valid, and your number for acceleration will be perfectly correct. This is not what you're looking for. But Fraser said, maybe you can use that acceleration to use another equation. That's fine. Let's try it that way. See what we end up getting for the answer. Let's use A is equal to delta V over delta T to get the acceleration first. It's 0 minus 16, so we get negative 16 over 8, which is 8.0 meters per second squared. Are we done? No, it's the acceleration. It's not what I'm looking for. But now let's use VF squared. 2, yeah. 16 divided by 8 is 2, yes. Who said that? Thank you, Mr. Mathematician. You are absolutely right. Negative 2, actually, right? So VF squared is equal to VI squared plus 2AD. Now this one's a tricky one to rearrange. We'd rearrange this to solve for delta D. The first thing we got to do is take the VI squared over by subtracting. Becomes VF squared minus VI squared. Why? Because it's added on the right-hand side. And then to get D by itself, I got to get rid of the 2 and the A. How am I going to do that? They're multiplied by D, so I divide, right? So it becomes VF squared minus VI squared over 2A equals D. Now that looks a little bit ugly, but let's plug our numbers in here and see what happens. That's 0 squared minus the initial speed was 16 divided by 2 times, we just found the acceleration. It's negative 2. Lo and behold, when we do this math, we end up getting 64 meters. Is it a coincidence we got the same answer? There are 2 or 3 or 4 or 5 different methods in a lot of these questions. As long as it's a group B problem and you pick a group B equation and you use it properly, if you get an answer, it's the right answer. It doesn't matter if it's the equation that I used to get that answer. Okay, if Fraser does it the second way, which takes quite a bit longer, right, and is a little bit harder, it doesn't matter. As long as he does it correctly, it will give him the correct answer, the same as mine. And I'll mark that correct too, even if it's not the simplest way to do it. All right? Clearly in this case, this was the easiest way to do this problem, right? But don't panic. If you do it another way and you get an answer, great. Go with it. Okay, don't necessarily look for that simplest way. All right, we will wrap it up with this for today. Okay, remember, you have an activity that's due on Monday, and you have 2 questions on page 48 that are due tomorrow. Remember, first thing you do, ask yourself, is it group A or is it group B? Then write down your givens, and then pick which of those 5, assuming it's B, which of those 5 equations fit the best, and then go with it. All right, that's it for today.